All right, we're going to talk about section 8.1, applications of integrals. Let's get started. So a lot of this section is review of things that we have touched on before, similar to the beginning of applications of derivatives, where we had talked about a lot of those concepts, but we're sort of tying everything together in kind of one section to make sure that no stone is left unturned here. So let's talk about, real quick, the relationship between position, velocity, and acceleration. You probably remember from last trimester, and it's come up since then, that s of t, if we call that position, then s prime of t is velocity, v of t, and then s double prime of t is equal to s prime of t, which is equal to acceleration, which is a of t. Okay? Then, if that's true, then working backwards, we get this. The antiderivative of acceleration is equal to v of t plus c. And then the antiderivative of velocity, some velocity function, will be equal to s of t plus c, some constant. Okay? And typically the c's are the initial velocities in this case and the initial positions in this case. All right, so then we go over here. Let's do some problems now. So interpret velocity. The following function gives velocity from 0 to 5 seconds. Describe the motion. Okay, so this is a question that definitely will show up on the quiz. It is describing the motion of a particle. And what we're going to do when we do that is we're looking at this velocity function, and we have to remember that velocity is signed. It's positive and negative, and it could be positive or negative, and that indicates whether the thing is moving in the positive or negative direction. And in this case, it's typically going to mean left or right when we're talking about just a particle moving along a line. And so what we're going to do is look at this graph and see, all right, well, when is the velocity negative? When is it 0? And when is it positive? Because that'll tell us when it's moving left, right, or stopped. So let's start just by looking at when it's negative. And that's when it's, again, when it's moving left. So it'll be moving left from 0 to 1.25 is where that crosses. I know it's a little difficult to see, but it's moving left from 0 to 1.25. So we're just going to write that out. This is an interval, by the way. It is stopped when t is equal to 1.25. That's when the velocity is 0. It's changing directions right there. And then it is moving to the right on the interval from 1.25 to 5. Okay, and yeah, so that's all we need to do on that. So look at the velocity function, figure out when it's above the x-axis, below the x-axis, or 0. That tells you when it's moving left, right, or stopped. Let's do another one. We're looking at the same function here, and we now have the initial position is s of 0 equals 9. So at time equals 0, the position is 9. We want to figure out what the position is at 1. At time when t is 1 second, and when t is equal to 5. And there's a couple ways that we can do this. I'm going to show you the method that is getting the position function and then figuring out what s of 1 is and s of 2 is. So, sorry, s of 5. Okay, so here we go. We're going to take the position function will be given by this, the antiderivative of t squared minus 8 over t plus 1 squared dt. Okay, so we're going to take the antiderivative of the velocity function. Okay, so s of t then, when we derive or antiderive that, is going to be equal to 1/3 t cubed plus 8 over t plus 1 plus c. Now we need to figure out what the c value is. And c, like I said, is the initial position. We don't really need to do the work, but you could put 9 in for s of t and then put 0 in for t and solve for c. But what you'll find is that, no, we do need to do that. I'm sorry. Got a little bit ahead of myself. Anyway, okay, so we do need to put in 9 for s of t and then 0 for t. So we get 1/3 times 0 cubed plus 8 over 0 plus 1 plus c. and that means that c is equal to 1. So now we have this position function, which is s of t is equal to 1/3 t cubed plus 8 over t plus 1 plus 1. All right, so there's your position function, and then from that you can just plug in 1, you can plug in 5, and it doesn't look like I even figured that out in previous years, so I'm sure that you can handle that. All right, next page here. Let's talk about interpreting velocity even more. So if we want to find the total distance traveled by a particle, remember we can figure out the net distance traveled by integrating under the velocity curve. All right, so just finding the integral from 0 to 5 would give us the net distance traveled. But if we want the total distance traveled, then what we need to do is take and find the total area under the curve. So in other words, this area down here, which is going to be negative, we need to take the absolute value of the velocity function so that we can get that area to be positive, and therefore getting the total distance traveled. So we are just going to set up the integral at 0 to 5. The absolute value of t squared minus 8 over t plus 1 squared dt. And when you put that in your calculator, we don't have any techniques for anti-deriving absolute values of functions. So when you put that in your calculator, you get 42.6 is the total distance traveled, right? All right, let's look at an acceleration function. Here we have the acceleration function is 2.4t, and we have a car moving with initial velocity of 5 miles per hour at the rate given there. And yeah, so the units are sort of weird here. It's miles per hour per second for 8 seconds. All right, so how fast is the car moving when the 8 seconds are up? All right, so we're given acceleration, and we want to know velocity after 8 seconds, okay? So what we're going to do for part A is take and integrate from 0 to 8 of the acceleration function and see what we get. Now, another way to do this is to find the velocity function and then just compute the velocity. But this way I think is a little bit easier. So I'll integrate from 0 to 8, and this will tell us well, I'm getting ahead of myself. Let's actually just do this. So this is going to be the integral from 0 to 8, 2.4t dt. And when you do that, you get 76.8 miles per hour. Okay, so this is the net change in velocity, all right? Just like when we, over here, if we had just found the area under the curve, under the velocity curve, we would have gotten the net change in distance, which would be the displacement. Over here, when we integrate under the acceleration curve, we're finding the net change in velocity. Okay, so this is not actually the final velocity, that's the net change in velocity. So, in fact, we're going to write that out. Actual velocity is equal to the initial velocity plus the net change. All right, so initial velocity was 5 plus 76.8, which was the net change. And so that gives us a final velocity of 81.8 miles per hour. So that's actually how fast the car is moving at when the 8 seconds are up. Okay, so part B says how far did the car travel during those 8 seconds? So to get that, we're going to need the velocity function. Without that, we can't integrate to, we can't anti-derive to position. So when I anti-derive the acceleration function, I'm going to get this, v of t is equal to 1.2 t squared, and then the initial velocity is 5, so I'm just going to add the 5 there. That'll be the c value. So then, if I want to know how far the car traveled, that's total distance. So to find the total distance, I'm going to integrate from 0 to 8 underneath of the velocity curve. So absolute value, 1.2 t squared plus 5 dt. And when you get that, you get 244.8. And the units here are sort of weird. They're going to be miles per hour times seconds. Okay, we can do a unit conversion to get this into distance. I don't know why I didn't. I thought in previous years I'd written that down in my notes. I guess I didn't. But the way you can think about this is if I start off as miles per hour per second, so it would be miles per hour per second, like that. When I get when I take the first antiderivative to get to velocity, I times unit-wise. I'm timesing by seconds. That gives me miles per hour. So that gives me miles per hour for my velocity. And then if I want to jump from velocity to position or distance, I'd be timesing by seconds again. So this unit here is sort of weird. Part of that comes from just the fact that we have miles per hour playing with seconds, and that's actually, if we were to convert this, that's how we would do it, is we would just put everything on a line and then get the time all down to either to hours or to seconds, so that we get just a distance, right? So let's look at another example here. Consumption over time. So from 1970 to 1980, the rate of potato consumption in a particular country was C of t equals 2.2 plus 1.1 to the t. All right, and so where t is the number of years since 1970, how many bushels were consumed from the beginning of 1972 to the end of 1973? What you need to understand here is that you're given a rate function. Okay, the rate of potato consumption. So if you want to know how many potatoes were consumed or how many bushels of potatoes, then you need to antiderive or integrate underneath of the rate function to figure out the amount. So if we want to know from 1972 to 1973, 1972 would be when t is equal to 2 to the end of 1973, which would be when t is equal to 4. So we are going to take and integrate from 2 to 4, 2.2 plus 1.1 to the t dt. And this is something that we're just going to have to compute in the calculator, and if you do that, you get 7.066 for your answer, but remember that this is going to be in millions of bushels, so, or I guess that's not given in the problem, but anyway, it's 7.066 millions of bushels. Last one. A pump connected to a generator operates at a varying rate. The rate at which the pump operates is recorded at 5-minute intervals for 1 hour, shown on the table. How many, should be gallons, this typo's been here for many years, should be gallons, were pumped in that hour. And so here's what we're going to do. The easiest way to figure out this question is to use the trapezoidal rule, and I'll explain why. So we have velocity, and then we have time. And so basically we have if we were to plot all of these points, we'd have the kind of outline of a velocity curve. We want to know how many gallons were pumped, and so that's the area underneath of that curve. And so using trapezoids connects all of these points together. All right, so we're going to use the trapezoidal rule, which would be h over 2 times y sub 0 plus 2y sub 1 plus dot 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 plus 2 y 2, so plus 2y sub n minus 1 plus y sub n. That's the trapezoidal rule. We're going to do that for the data that we're given here. H, remember, is equal to b minus a over n, which is the number of subintervals. So let's find all of those pieces here. So I have a is equal to, and then h is going to be 5. So b minus a is 60 to 60, and then we have what do we have? 12 subintervals, I think. Yeah, I think it's 12 subintervals. So we end up with h is 5 over 2. And then our first y value is going to be 58 plus 2 times our second y value, which is 60, plus 2 times 65 plus dot 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 plus, and then your last thing will be 63, which is the last point down here. You just put all this into Desmos, into your graphing calculator, and you end up with a equals 3582.5 gallons. All right, so this section, lots of application of integrals, obviously lots of word problems of different types, but all kind of working with velocity or rate functions generally, and working back towards, amounts, or position or distance or those kinds of things. So that's it for section 1.